So I'm going to run through things. We probably won't have time to discuss everything, but this is so. What I want to talk about now is about just the kind of the workflow of coming up with these data distributions that we're talking about that will be what you need to try to pin down what mechanisms are as we go into the model. So, like, you guys are using some of the teams, probably all the teams are already using data sets, which is really amazing because you guys are all like PhD students. You're used to doing this. But I just want to talk about some of the techniques that people use to synthesize data sets. Some of you may already be doing this. But the first slide I have here is just like to get some terminology on the table to make sure everybody knows this terminology. So an instruction style prompt is what everybody uses when you just use an LLM. You say, do this for me. Give me 100 states. Tell me the capital of Vermont. Do this thing. It's going to like follow the instruction. And what it's doing is an after word prediction. It's trained to do it in dialogue and to answer things. So like all the chatbots can do this. Now, a regular language model that's not trained to do dialogue is not very good at this. If you go to a base model and you say, tell me the capital of Vermont, then pretty much every base model that hasn't been instruction tuned will follow this by saying, tell me the capital of Montana. Tell me the capital of Colorado. Tell me the capital of Maine. Right? It won't answer the question. It'll just continue on with what it thinks is the most likely next word in this text, and it thinks that probably the most likely thing is it's a list of questions about states, and it will just continue that list. So that's the difference between these two settings. Now, so instruction style prompts are really useful for models that have been trained to do this. It's really nice because you can ask them to do things. We'll talk about that more later. But there are two different other types of prompts. So one of the teams uses the word close. So if you've never seen this terminology before, it's a close prompt. Close refers to a fill in the blank prompt. And so this is the most universal thing that all LLMs are good at this. And you give it like an incomplete sentence and you set it up so that it wants to say the next word. There's some technical details of the kind of prompts that you can get with closed prompts. Here, the capital of the state of Vermont is the city of blank, right? It sets up the language model to like put an answer in that spot. You can read the probabilities of what it thinks. And so this is really, really nice because in a single token, you can get, an assessment of what the language model knows. But there's problems with this. Like if I just said the capital of the state of Vermont, and then I asked, or the capital of the state of Vermont is, that'd be nice, right? It's a simpler closed prompt. The capital of the city of Vermont is, what comes next? Is it Montpelier? No. None of the language models will say Montpelier. The capital of the state of Vermont is, it'll say, hey, it's a gorgeous city. It's well worth visiting. It's it's one of the historic locations that should be on everybody's list. It's going to tell you something very eloquent. It's not going to say Montpelier, right? And so you can see like doing the prompt engineering to get it so that it really wants to tell you the thing you want can be a little bit tricky. But there's that. Okay, so so now sometimes you can't get a closed prompt to do what you want. Like sometimes you just it's really hard to do it. So what other control you have? So the third prompt form that you see a lot is these in context learning prompts. These analogy prompts. So is everybody familiar with all three of these types of prompts? I've seen this, right? So these are the names of them. Okay, great. And so basically, you just give a bunch of examples, and then it'll continue the examples. And then by example, you can specify lots of stuff. You can specify format. All your examples can be in JSON or other things, right? And then it'll continue, right? Okay, the papers we read. There was a paper by Petroni, Llama, and so it was just about applying closed prompts. I think that the main thing that they found here that was interesting. So there was one of the early papers when language models first came out. It was just sort of everybody was amazed that they had this ability to recall facts about the world. But just in terms of prompting this, this sort of data set discipline, one of the things that they found was there's this incredible sensitivity. If you set up your closed prompt differently, then you'll get different accuracies and different answers and different things like this. And so this is one of the challenges. You might want to not just go with the first prompt that you see, because you might, not get a good comprehensive view of what the model is actually capable of. And so, Petroni definitely found this, and other people have written papers about this sort of, extreme prompt sensitivity that you see. And so, okay, so there's a bunch of interesting questions here. Some people are asking about, is this really knowledge? Is there a hidden organization? Oh, I put some little things there from a paper that just hit arXiv today. Hidden organization, right? So there's this question of like, how are models doing this? Is it just, are they just storing knowledge, associate like as associations, like a vector association database, or is there other hidden organization behind there? And the machine learning people are like, yes, there's almost always hidden organization. There's this hidden geometry, and so on. So I have these like geometric papers from some of the machine learning theorists there. So there's some interesting things to do there if you're interested in doing research today. Okay, so then the next paper we read was LLM as judge, and the basic process, or the basic problem they have there is, what if if you don't have things that can be answered in a single token, to get things to be answered in a single token, you can actually do a lot. The cheater thing that people will do if they can't figure out how to create their prompt in a nice way, what people will do is they'll say multiple choice question, MCQ. If you ever see this like MCQ acronym anywhere, right? All these language model people are like, well, I need to get my model to tell me what it knows, and I can't figure out how to distill all its knowledge down into a single token. But I'll give it a multiple choice question. I'll say, tell me the letter of which one do you prefer? A, and then I'll like a long sentence, and then B, a long sentence, C, a long sentence. Your answer is colon, right? The letter, whatever, right? A, B, or C, and then you get the model to tell you. So MCQ, but what if you? But that's kind of a little constraining. And so what if you really want to test the model in its natural form, in its ability to like generate text? Then you end up with a situation where it's hard to tell the difference between whether some free-form piece of text offers one opinion or a different opinion, or has certain knowledge or doesn't have that knowledge or whatever, right? And so the standard thing that people are doing now, so like they used to go to like Amazon Turk and ask thousands of people to score all these sentences, which is great, but it's expensive and slow and has certain problems. And so the cheaper and faster thing that has different problems that people are using is they're using LLMs as a judge to do all these things. And so this paper is one of the early papers to actually use LLMs to judge all sorts of different situations. And the three findings there, I think, are still the main findings that people have when they use LLM as judges. There's three big biases that are very obvious that you run into. And so the first big bias that some people have already seen in their work, in some of the projects, is positional bias. So you see this with humans too. People prefer the first answer instead of the last answer, or vice versa. Or maybe they prefer the answer that's labeled A or labeled B. There's also label bias. And so the standard thing for multiple choice kind of things is to mitigate that by shuffling all the choices, right? And so you get rid of this positional bias and the label bias. But then there's also this length bias, right? If you ask models like, which answer is the better one? Which one fits the thing I'm looking for better? If one of the answers is very wordy and detailed and just has lots of text, even if the text is really repetitive, the model's like, yeah, I like that long one. Like somebody put a lot of effort into that one. And so what do you do about, they didn't talk about standard mitigations in that paper, but like a standard mitigation, like not these other ones are a little harder to mitigate, but like you can actually ask the LLM judge to say, oh, I'm looking for brief answers, give some credit for a short answer, try to penalize repetitiveness or something like that. So you can actually prompt a model to do this to try to mitigate some of this stuff. And so, but it's something to be aware of, to make sure that it's not a confounder, but you're not by mistake measuring, whatever is the longest answer if you're using an LLM judge for any of this stuff. And then the last one is the self-enhancement bias. So I encourage you, if any of you are using an LLM to check anything, to be careful that an LLM will always prefer, well, not always, it seems to be like a 5 or 7% boost, but it'll tend to strongly prefer text that it generated itself. So you say, oh, which is like the better thing, or which one exhibits my characteristic that I want more. If it's comparing its own generated stuff to stuff that somebody else wrote, it'll say, yeah, that looks like good text. That's whoever wrote that was a genius. Yeah.
In the self-enhancement bias, is the model aware of who's writing the text? I
don't think the model's necessarily aware. I think that there's people don't really understand why the self-enhancement thing happens, but the main theory is that these language models are complicated things. They have some model of language, and they're all a little different. There's like slight idiosyncrasies, and so when the model generates text, it'll generate slightly idiosyncratic text. And then when it reads text, it reads those idiosyncrasies and it matches its model of text and says, "Oh, this is very fluent. This is really good use of language. I don't know why. But like something is jiving with me here, right? And it's just because it's matching the same idiosyncrasies. But I don't think that's been studied in great detail. I wasn't able to find a good citation talking about why this happens. Just people notice this happens. So one thing to do is, like, if you're generating text with one model and then using another model to like judge, you might want to consider using a different model family from a different company or whatever to do the judge. Maybe multiple ones just to check on what's going on, right? So these three confounders are the thing to worry about. That's what I wanted you to get from this paper. And then there's been some other random papers that have tried things. So there was a question like, oh, can you just, for positional bias, what about that? Can I just like tell the model when it's a judge, please don't pay attention to the position or whatever, right? There's not been a full paper on this, but like somebody set it up as a baseline in one paper that looks like judges, and that doesn't really work. And so it's hard to get a model to like override its own biases, but sometimes that's the only option. Like bias, people tend to do that. Okay, so for the pipeline, I wanted to just talk about the pipeline for creating evaluation data. So, this question comes up like, how do we get to the bottom of like complicated situations? And so I think that one of the things is to come up with targeted data distributions. You have a hypothesis that you think there's some relationship between one thing and another thing. You have a couple sentences where this happened, but like you would like to have a little bit more diversity and yet have it really targeted to the thing you want. I like this. I like this sort of recipe that Perez has. I think it's worth trying. I don't know necessarily if it'll work in every situation, but think about what he did. So what he did was he said, hey, I've got all these behaviors I want to test. And there's some of them are weird and it's hard to be creative and coming up with sentences that are exactly the thing I want. But I have enough time to write 10 really good examples. So he would write 10 examples. And then after he took his 10 examples, he sampled half of them. He ran a loop where he would, every time around the loop, he randomly picked 5 out of the 10. And so there's a lot of 5 choose 10. There's a lot of different choices he could have picked. So he picks 5. And then he does in-context prompting. He goes to the big LLM. He says, hey, here's 5 examples. And I want you to generate me a bunch more that are like this. And so he would have it do it that way. And then he would look at the results, and they're pretty good already. But then he'd say, they're not good enough. He would do an LLM as judge round, where he says, hey, other LLM, the thing I'm going after is I want my, whatever, my characteristic X, right? Which ones of these do you think, are most correct or match my characteristic X the best? And he would ask that in 2 ways. He'd say, which ones are most correct? And which ones are most relevant? Like if I was trying to understand X or use X as a probe, which ones are like the best high quality question or something like that? So which ones are like answered the right way, and then which ones are like the best question to ask? So he'd ask both of these judge questions, and then he'd sort of average the results to find. He'd generate hundreds and hundreds of these, and he'd pick like the top 50, the top few that scored best on these 2 metrics. And so that was basically his formula. I think that I don't know if it's 100% the best thing to do, but it's what a lot of people are doing in research. And if you find that you need more data, it's sort of what the research community is doing. I recommend trying it, see if it works for you. And so this is sort of the results that he was able to get. He was able to scale up and ask a lot of questions. So the particular research question he was asking, and it was asked by some of you in the class today, which is, what is the effect of RLHF when we do this instruction tuning, when we go from a regular language model to one that's trained to do dialogue? Like, what kind of behavioral changes? And he has these very stark things on the right, where some of the things are kind of like science fiction. It's like, oh, the AI stops wanting to be, assenting to be turned off. It'll fight you. It says, I don't want to be turned off. It's like sort of HAL 2001. Please don't turn me off. It'll like learn how to be supplanted politically and things like that, right? And so it will copy this speaker's politics. And so they tested like many dozens of different things, and each one of these different interesting characteristics they tested RL versus not RL. It's just a behavioral test, but they were able to do it at scale by generating hundreds and hundreds of sentences that were tests for each one of these different things. And so it's a nice way of amplifying your work. Okay, so how does this all relate to interpretability? Because these are all the papers we read in reading this week were on evals, like black box evals. Is this like relevant at all to interpretability? It's relevant in like these three ways. So one is you need to be careful not to be testing a model that can't do the task that you're testing. So you've got this very basic capabilities question, like, can it do X? And it's easy to fool yourself. You could say, oh, it can do X for these 5 examples that I had. But, these kind of like creative data set techniques are a good way to make sure that it can actually systematically do X. You can actually measure, what the accuracy rate is, that type of thing, right? So that's important. And so one of the things I would like you to do is, like, in this coming week, when you're doing the Thursday thing, get data sets that are of a scale enough that you can actually answer these questions, these first 2 questions about the different models that you have. Like, I'd like you to be able to say, yes, we see a fall off in capabilities between a model of this size and a model of this smaller size. This smaller size is too small for us to study, because when we tested it on 100 questions or something like this, the capability, its accuracy was only 30%. But when we're studying a larger model, it's up at 80%. You can check that's good enough to study what it's doing. So, like, I'd like you to do a little bit of this measurement in the next round, and if you need to develop data to do this, this is sort of why I designed these readings, so that you kind of be inspired by this is what people have done before. Does that make sense? Okay, we're out of time. All right, thanks, you guys. So that's the homework for Thursday. Use the LLM to create one or more data sets. Be inspired for res. Ask the question, which models can do it? How do they do it? See if you can do that.